Hi, everyone. Let's get started. Welcome to this webinar. I am Wim Oudenaert. I am CEO and co-founder at AM Team. It's my pleasure to be welcoming you to this international webinar. We have a lot of people signed up for it. It must be a very hot topic, and it is a hot topic, net zero, nitrous oxide emissions. A lot of people are talking about it, but also acting on it. So that's the good thing. A lot of things are moving right now. So this topic, it's clearly alive, and that's what we see in the wide array of people here from different parts of the world, but also different types of companies with different types of backgrounds and activities. So welcome. So the title of this webinar is Wastewater Treatment Plant Maximization in a context of new regulation and net zero. The water industry is never stagnant. There's always something new. There's always more stringent effluent limits lurking around the corner. And then suddenly also now we have to really look at net zero. So balancing all of these things can be quite challenging. And we try to really bring that into this webinar today. So what is the agenda? What is the menu for today? I will start with a small intro of this webinar and put the scene a little bit. So I will set the scene a little bit on the nitrous oxide emissions. And then we will have a very exciting lecture by Ioanna from Evides Industriewater. So she is our guest speaker. I will introduce her a bit later. And she will be talking about their journey at Evides Industriewater, but also full-scale mitigation example. So she will be presenting quite a bit of slides that have valuable information. And then we have Pieter Vlasgaard from our team. He will be zooming in further on the application of modeling, because we believe it can really, and it is actually playing an important role already in that puzzle. And I will end with the general conclusion. So there will be polls in this webinar, so you will be able to vote during 2 poll questions. If you have any questions and we really stimulate you to ask a lot of questions, please use the Q&A window. So if you go over the screen, you can see a Q&A button. So that's the place to be where you can actually ask your questions. You can ask them anonymously, or you can use your name. You can choose. After the webinar, there will be a survey. So if you close Zoom, normally there will be a pop-up window with the survey. And for the people that have not done it, they cannot escape it, because you will receive an email tomorrow as well from Zoom asking for this survey. Okay, this will help us a lot. We value that really a lot. Small introduction, one slide about AM Team, just in the case you don't know us yet. We provide modeling and data services and digital twin solutions to the water industry worldwide. Specifically, we focus on big challenges. It is not only nitrous oxides, it can be also a lot of other topics, including reuse, micropollutants, wastewater treatment, enhancement of drinking water treatment plants, digitalization. So all of these things together. We are headquartered in Belgium, but we have a global reach. You can see some of our customers on this slides. They are quite international. And we assist those customers in the planning stage, in the design stage, in the operations stage. And now digitalization is a topic on its own as well. So we also built digital twins for these customers. And we work very closely together with all of the stakeholders. So this means engineering companies, software companies, sensor companies, utilities, and users. So we work closely together with them, because our core focus is building these digital twin models and the computer models. Yeah, and then we plug into other, we work with other partners and solutions. So up until now, we have served our over 100 clients throughout the last 8 years. So it's really adding up a lot. And specifically in the area of nitrous oxides, it is growing. So I am Wim Oudenaert. I'm CEO and co-founder of AM Team. And I will be presenting part of it today. But then we have another presenter who is my colleague, Pieter Vlasgaard. He is the VP Sales and Solutions within AM Team. Pieter will be zooming in on some topics of the modeling and the applications at full scale. And then we have our guest speaker, Ioanna Gkoutzamani from Evides Industriewater, and she will be going over their journey and a full-scale mitigation case example. So welcome, Ioanna, as well to this webinar. All right, we have also a lot of other contributors. It is Giacomo, Roberta, Usman, Constanza, Harun, An. So these are people from our team that have really worked behind the scenes actually to make these things happen. So it's always quite some effort to put a webinar together if you want good quality. So we will start just as a test and also to know who's in the audience with the first poll. So normally on your screen, you should be seeing a first poll. Which type of organization do you work for? Are you a consulting engineering company, water utility, industrial end user, technology vendor, research institute, or academia, let's say, or other? So the votes are coming in. We have, yes, 50% of you answered, 60% have voted. It's coming in. All right, I will end the poll in 3 seconds. Yes, and show the results. So here are the results. You can normally see them on your screen. The majority here is water utility. So these are typically the people looking for solutions and wanting to quantify these emissions and want to mitigate them. But you can also see that we have consulting and engineering quite involved, and also research institutes quite involved. So it's an interesting mix of people here. So thanks for voting. All right, let's continue. Getting a grasp on the process emissions. I'm calling it a grasp because it's a beast with many heads, and a beast with many heads is difficult to catch with a net. So you really have to think about it. And process emissions is something like that. However, we are, of course, getting there slowly and gradually, but it isn't the most easy question, let's say. Why is it important? Well, I should not introduce this anymore. I think that nitrous oxide is a very strong greenhouse gas. It's approximately 300 times stronger than CO2. So you don't have to emit a lot of N2O to have a very big impact. And that's why nitrous oxide emissions, of course, it's not a secret anymore right now, are easily contributing to a very big chunk of the emissions of water treatment. So it is important to do something about it. And also, if you want to do something about the general carbon footprint, it is actually also business-wise very efficiently and smart to focus on N2O, because we can do something about it, and it is a very big contributor. So it's very smart to focus on nitrous oxides. Then you can say, okay, if we talk about quantification, why not use some fixed emission factors? We have published values out there. Well, more and more utilities already realize they are not plant specific, while we all know nitrous oxide is plant specific. They are inaccurate to highly inaccurate, and they also do not reward mitigation actions because they solely look at the influent nitrogen. Just imagine you do a very good job with controlling your aeration and you reduce your emissions, but your influent is not changing. You might still have the same emission factor. So there are a couple of flaws here, and this is why many utilities and an increasingly number of utilities are looking for site-specific action. And action means you start quantifying or monitoring on sites, you start modeling, you start mitigating, you are starting to think about this site-specific nitrous oxide emissions. When it comes to those actions, there are actually 3 big groups right now utilities are looking for. That's what we learned when talking to a lot of utilities. The first one is quantification. You want to know how do you actually have an issue and how bad is your issue? What are we emitting and what are the emission dynamics in long term, short term? Then the second question is, okay, when we have those emissions, we should understand what is causing it and what is the potential to reduce so we can make a plan. So this is the understanding phase. And then we also have mitigation, which is the end goal, in fact, how to reduce our emissions. So I will repeat again, even though quantification and understanding are very important, the real end goal is mitigation. We should really not forget this. So when we look at the mitigation actions and when you mitigate nitrous oxides, it is important that you don't forget the core needs of a utility. You are still treating wastewater, and that is there for specific reasons. you want to meet a certain effluent goal with a certain plant efficiency. And of course, recently now we have to juggle this third ball, a football or a juggling ball of the emissions. It is important that if you reduce emissions, of course, that you don't hamper process efficiency or effluent quality. And the good news is, this is what we call the 3 E's. The 3 E's can be handled together when you are mitigating. And Ioanna's example will also illustrate this, okay? But this is very important. The core focus of wastewater treatment is to treat wastewater and achieve a certain quality with a reasonable cost and efficiency. And of course, with as low as possible emissions. That is super important. So I will quickly introduce the project now that we worked on together with Evides Industriewater. Ioanna will start talking in a few minutes. This is about a full-scale plant in the Netherlands, and I want to provide some context that is important for you to get the case very well. The first thing is, Evides Industriewater was actually in the process of quantifying their emissions already. They were quite an early adopter. They already do actions for quite a while. And at the very moment that we started working with Evides Industriewater, they were already measuring at that site for 1 year with liquid phase monitoring. These are the Unisense sensors. This is a BNR plant, biological nitrogen removal. This means you have denitrification taking place. But this webinar, despite a lot of the, the mitigation actions will be on, for example, the denitrification. Despite that fact, people here in the webinar that don't have denitrification can, of course, also learn from that. I just want to highlight that. See it as a generic mitigation learning experience, okay? And this brings us to Ioanna, our guest speaker. I will quickly take my notes here so I can properly introduce Ioanna, if I can see my notes at least. So Ioanna is a process engineer at the R&D team of Evides Industriewater. She is focusing on various topics, including reuse, resource recovery, and of course, nitrous oxide emissions reduction and research. And her background is civil engineering from Aristotle University in Thessaloniki in Greece, with a specialization on hydraulic and environmental engineering. And her master's was in Delft in the Netherlands in water management. So she also studied at Delft University of Technology. That's a quite well-known institute, of course, as well. So, Ioanna, we are very curious about your presentation, and I will
Perfect. Thank you, Ken. Hello, everyone from my side as well. As we explained, we've worked together in Evides Industriewater with the AM team to quantify and mitigate laughing gas emissions, nitrous oxide emissions in one of our full-scale plants. We have prepared a few slides to take you with us in this journey. First, a few information about Evides Industriewater. We are providing water solutions for customized water solutions for industrial clients, and that can be processed water for several processes of industries like cooling, but also demineralized water and wastewater treatment. We are focusing a lot in options for water reuse, for resources recovery, and this is also the focus of our research department, R&D, but also we are trying to find ways to optimize our existing processes and minimize the energy use or lower our N2O emissions. And this project belongs to that part of the company. So in general, our environmental policy is that we try to reduce our CO2 footprint, use more renewable energy, and reduce our emissions, and of course, not contribute to water scarcity. So have better recoveries, reduce water as much as we can, and then reduce our pollution to the environment, to the water bodies. So there are ongoing projects for all these fields. And then specifically for the emissions, the greenhouse gas emissions from wastewater treatment plants, the main three contributors are CO2 emissions, methane, and nitrous oxide. And the nitrous oxide, based on literature, is one of the biggest contributor, as we mentioned. But then this is something we have already seen. in our specific case, where we have a 2-year campaign or measuring campaign. We mentioned one because when we started collaborating with AM team, it was 1 year. Now it's been 2 years. And if you see the pie of CO2 contributors for this specific plant, you can see that laughing gas, nitrous oxide, is 50% of the total emissions. And if you take also into account the demon, it's a bit more. Then the aim of this research was at first to quantify the emissions, to know our baseline, knowing what laughing gas is being formed at which moments. Thereafter, to understand why it's being formed. So what are the formation mechanisms and what factors that we might be able to change contribute to this formation of laughing gas. And finally, of course, try to identify mitigation measures and implement them. So a few information about this industrial site. It's a conventional activated sludge system with a denitrification and nitrification. The effluent, even though it's called industrial plant, it is similar to municipal, but it's more concentrated, much more like 5 times more concentrated than typical municipal, and has less COD compared to a municipal. And also the patterns are different. The daily and weekly patterns are different than a municipal plant. And of course, for a laughing gas research, the focus was in the denitrification and nitrification tanks, specifically here highlighted with red. Then the approach followed. First, as we said, we wanted to measure. So we chose for liquid phase nitrous oxide monitoring. That's already happened. Then we followed with data analysis from our side, and also in collaboration with the Brunel University of London, we had a multivariant analysis. And thereafter, we proceeded with model-based root cause analysis with AM team, and with model-based mitigation strategy testing with the AM team. And now that we have found our mitigation measures, that I will come back to them later, we are in the phase that we are trying to implement them in full scale, and thereafter continue monitoring to be sure of the effect. Then, for the measurements, we chose the unison sensors because they measure in the liquid phase. We know that measuring in the gas phase might be more accurate when it comes to the actual emissions estimation, but then if you want to identify mitigation measures, you need measurements inside the water, because you want to know and be able to compare the moment you see a formation of N2O, what else was happening at the same moment. Because if you measure in the gas phase, maybe what is being emitted in the air at that moment might be formed a bit earlier. Then let's go to the main outcomes. So 2 years of measuring campaign from December 2021 until January 2024. What we have identified, okay, the average formation factor with coincide comes really close to the IPCC number, around 0.016 kilograms of laughing gas per kilogram of ammonia being treated. But this is the average of the year, or the average of the 2 years. If you take different periods, you'll see that at some periods it will be much more, and at some periods it will be much less. So there is a seasonal profile with higher formation when the temperature of the water goes down. So during autumn, winter. And thereafter, we also found a daily profile that it was repetitive, and then a mitigation measure that was identified and tested with a model of AMT. Now, before we go into details of what all this means, what all these things mean, let's remember what is N2O and how it's being formed during nitrification and denitrification. So here we have nitrification from ammonia to nitrate, and denitrification from nitrate to nitrogen gas. Then you have 3 main pathways. In the nitrification, it's from the order of through hydroxylamine oxidation, when you have high DO and high ammonia loads incoming to your tank, or you have the other pathway that is through A or B denitrification. So when there is low presence of dissolved oxygen, and high concentration of ammonia or accumulation of nitrates. And then in the denitrification side, in the heterotrophs are able to produce N2O, but also consume them because it's an in-between step during the nitrification. But to do this, they need COD, carbon source. And if you have carbon limitations compared to the amounts of nitrogen that are coming into your tank, then you might stop in an earlier step of this process, either stop at NO2 or N2O. And both would end up in the formation of N2O because also accumulation of nitrite will end up by the AOB denitrification becoming nitrous oxide. So this is how it was formed. And now let's have a look at the daily repetitive profile. So you can see here, well, one moment. Better like this. You can see here the influent water. It's 5 days, and whenever the influent water will go down, also the incoming ammonia, the blue dark line here, will go down as well. But then you will see that the nitrification zone, the nitrate, will go up because it's related to a previous peak of ammonia, since there is internal recirculation. And at those moments, since the incoming influent goes down, also the incoming available COD for the nitrification coming with the new influent goes down, and we need to have an external carbon dosing. And we had that. But then the way it was being dosed, it was not optimal for full for N2O formation. So at certain moments that the COD over N ratio will go low, you will see an N2O peak in the brown line on the top. And that sometimes will happen with any other contributing factor, but sometimes you will also see a dissolved oxygen peak because of a certain situation in the tank. So we realized that the biggest trouble for our process seemed to be the not optimal carbon dosing system, but also it could be partly by the dissolved oxygen or by the seasonality. So then we wanted to realize what is actually happening with some external help, and this is how we went to Brunel University, where they did a multivariate analysis, and their main outcome was indeed there are 3 contributing factors, and the one that has the biggest effect was the COD C over N ratio, followed by the temperature, so the seasonality effect, and then the dissolved oxygen values. So for the seasonality effect, we could discuss it, but then there are not many things you can do to act on it. But whenever you, at this phase of the knowledge we have in literature, at least, because I know an interesting PhD research that's taking place in TU Delft right now relevant to this subject. We hope for results. But for the other 2, we can act on it. We can optimize our carbon dosing, and we could optimize our aeration. And this is how we decided to proceed with AM10 and see how we could optimize it. But first, we needed to do the CFD modeling, where they take into account the physics and the biokinetics, and they recognize the laughing gas hotspots in your tank. And that was quite viable because, for example, in one of the zones, you have the anoxic and the aerobic zone. We saw that in the aerobic zone, we weren't able to pinpoint the best place for measurements. And then after this research, we were able to find a better location for our sensors. And then this CFD model, kinetic model, it gives you the base to proceed to the dynamic model that is based in ASM modeling, activate sludge modeling, and then include also spatial information. And with this dynamic model, we were able to check virtual mitigations, to test virtually mitigation strategies. Now, let's see the results. The CFD kinetic model. In the left picture, you can see the dissolved oxygen concentration in the tank. Just to remind a bit, these first 2 lines are, because the water comes this way, that is the inlet arrow, it's the anoxic zone, and it's followed by the aerobic zones. And then you can see that there are very, very low dissolved oxygen levels at these 2 zones, while the end of the aerobic tank, the oxygen goes, the aeration was higher. And then there was also quite some dissolved oxygen returning with the internal recirculation. And on the right picture, you see in relationship the N2O production and consumption throughout the whole tank from all the pathways. And then we could see some net production of laughing gas that it was caused, for example, by the returning oxygen, so AOB denitrification at the point of the return. Don't be confused by the intense two colors, because these are from the main production and reduction of laughing gas during denitrification. It's around it. Then you also have N2O production due to carbon limitation. And then we could see also N2O reduction due to low dissolved oxygen during aeration, and that's again AOB denitrification. And when AMT took all these parameters together and quantified them, we were able to see that the biggest contributor to the N2O formation in this specific case was the nitrifier denitrification, so AOB denitrification, but from incomplete denitrification and accumulation of NO2. So we will have lack of carbon that will result to incomplete denitrification, that will result to accumulation of NO2, and this NO2 was everywhere in the tank, and AOB could take this NO2 and make it nitrous oxide. Then this is the focus of the results, only focusing on the AOB denitrification and hydroxylamine oxidation pathways. And you can see the peaks of AOB denitrification that they were mostly here, that we were going from a low to a higher dissolved oxygen concentrations. And as a total amount, it was much higher compared to hydroxyl oxidation, that it happens partly in the end of the tank. And we proceed to the dynamic model, where you can see the model's prediction with the two lines, while the dotted green points are the actual data of those days. And the model with our actual data had quite a well fit, even though the model overestimates the formation. We thought that for the purposes of our application was good enough to proceed to test mitigation measures. And then you can see here that there is no actual measurement happening, but also the model does a prediction information that there was sufficient carbon to consume all the N2O and become nitrogen gas. While here that we had the peak of formation, it will be, we will also see a carbon limitation in the water based on the model. And thereafter, we decided to test different scenarios. So on the left graphs, you can see the carbon dosing trends we tested. First one being the base case. Then the middle graphs are the laughing gas concentration. The model is the continuous line, while in the first graph of the base case, the orange dots are the actual data. And then you can see the carbon dosing need, so the amount of carbon that we had to dose per day, and the expected emission reduction compared to the base case in the right bottom graph. The most interesting scenarios, and I'm going to focus a bit on them compared to the base case, was scenario 3 and scenario 5, where we would dose carbon in relevance to the amount of nitrogen coming to the denitrification zone. And in scenario 3, it will be just related to the amount of nitrogen coming to the denitrification zone. But in scenario 5, we decided to also include the COD that is coming with the influent. Because in scenario 3, we would end up to having to use more carbon compared to the actual base case, while taking into account what's coming with our influent, result in reducing also the carbon use by 10%. And these two scenarios resulted in 88, and actually for the last scenario 5, to 80% reduction of the N2O emissions. And you can also see the patterns that it's compared to the base case, how much reduced the laughing gas formation is. And finally, this is extra related to 10 to 15% effluent, total nitrogen in the effluent reduction. So conclusions and next steps. We have also realized, as we mentioned, that laughing gas can be reduced, but never can be to zero by taking good care of your bacteria. So you have to avoid having peak loads or too high or too low dissolved oxide and sufficient COD. But also we have realized that N2O formation is plant specific, and you need to measure in your location to understand what's happening. For our specific case, incomplete denitrification in combination to AOB denitrification were the main pathways. And with the help of AMT modeling, we were able to validate our expectations of why we have formation, and to test mitigation strategies that result in an 80% and find out which is the most optimal one, and that result to 80% laughing gas emissions reduction, 10% of reduction of external carbon dosing, external carbon dosing, and then finally 10 to 15% effluent reduction in the effluent total nitrogen. So the next steps is to upgrade our carbon dosing installation and evaluate, and we are right now working on this. And we proceed with research in our other Evides Industriewater locations. So that was my presentation. Thank you for your attention, and we have some time for questions.
Thank you, Ioanna. Thank you for your story. Some questions are coming in. So thanks for the audience for asking a couple of questions. Feel free to ask some more. First question is here, for example, a person that only saw the data in the base case, and of course we have mitigated with the model where you didn't have data for yet because you are still implementing these measures. Why aren't there any measures in the other scenarios? That was the question. But actually the big question is, how do you look at the future after implementing those measures, I think?
Okay, so let's go a few slides back. There are no data, orange dots in the other scenarios.
Correct.
Yeah, because this is a model, so the actual measurements is only in the base case. And we see that the model that it's the blue line coincides quite well with our actual data. And then the rest of the scenarios, you can imagine that the actual data are at the same moment, but it's the model virtually expected how it will be, but we didn't test them in full scale. We are going to implement it in full scale once we upgrade our carbon dosing based on scenario 5, and then we can validate in real life our expectations. But we believe it will work, and we are going to do a really big investment to implement, because our carbon dosing upgrade needs quite a big investment, I would say. I will stop it there. Because we have validated this outcome from our own observations, from a statistical analysis, but also from a dynamic model that takes into account the biology behavior.
And then related to those investments, Ioanna, we have another question. What is the main driver for Evides Industriewater to really work on this and also even invest in this?
Laughing gas reduction.
Correct.
So in Evides Industriewater, they take it quite seriously right now. We have dedicated studies to methane and nitrous oxide formation in all of our plants, trying to understand where we stand and wherever we can to find mitigation measures. We have a rule, an internal rule that says, okay, for every mitigation measure that you can reduce a kilogram of N2 or a kilogram of CO2, so you have to relate your N2 or methane to CO2, you are allowed to invest 333 per ton CO2 reduced. So the driver is to reduce our emissions. As much as possible.
So you put a value, You put a value.
And it's quite high.
Yes. I see. And then,
334 euro per year with an index of 3.5%.
And then two additional questions related to the scope of your work. Huh? One question is, did you also conduct gas measurements once or so to compare with the liquid measurements?
No,
That's
we
the first question.
never hit gas measurements.
Yeah.
Mostly because of time limitation and budget limitations at the phase of the research, because gas measurements are always quite expensive compared to liquid measurements, that they can be ongoing for a really long time. But then the second point is that the gas measurements, it will show you how much is your emission, your actual emission at certain moments, but it doesn't indicates why it was formed. And for us to find mitigation measures, it was more valuable to measure in the liquid and be able to relate other parameters that are changing, because you see fluctuation in a daily pattern. A gas measurement will give you information of the whole day, I would expect.
Yeah. And then we have another question on really zooming in here on these graphs. That's maybe a last question. We can certainly come back to the questions later for the audience. Scenario 1 seems the best when you look at the zero. Can you explain a little bit more why
Yes.
there's 5?
Yeah, but of course, scenario 1, but it was a huge amount of COD dosed, that if you see on the carbon dosing needs, you dose not more than double what you used to dose. So of course, when you're trying to reduce a certain factor, you have to take into account that even if you have to use more carbon, it has to make sense, because this carbon is also purchased and produced and transported and has CO2 effect as well, CO2 footprint.
Sure.
So that's why we not consider.
Yeah. That was a scenario we tested to see the boundaries of the system as well.
Exactly.
Yeah. Okay, good. All right. I think we will leave it here for now, Ioanna, because we still have some content. But at the end, we might come back because there are a lot of questions. So you clearly triggered some interest. That's very good.
I'm glad. Thank you.
Thank you, Ioanna. And thanks for the audience as well for asking plenty of questions. So you can keep putting them on the Q&A window, and they will be monitored by our team. So we will come back to some of them. All right. So we have another poll coming up. This one. In which stage are you right now? So we have seen a lot of utilities and industrial end users. So in which stage are you? You are exploring the topic of nitrous oxides, early stage, let's say, or you already are quantifying your emissions, or you are already taking concrete measures to mitigate, or you are in another stage. That's also possible. So the votes are coming in. 50% of you have voted, 60% have voted. I will wait until we reach 70%, maybe a few more. Yes, we have reached 70%. I will end the poll and share the results. So here you can see the results. And many people are in the early stage. That's what I was also expecting a little bit, either exploration stage or quantification stage. But these things are shifting, and you can see a huge proportion of people that are already in quantification stage. So it's about 50-50, let's say, learning, quantification, and some people are in the mitigation stage. So thank you very much for voting. It's always interesting to know, and of course these things will shift throughout time. These results. Okay, then I will now pass it on to my colleague Peter, who will be taking us more into the modeling as an important part of the puzzle, and concretely the practical application potential at full scale. So Peter?
Yes, thank you, Wim. And hello, everybody. So indeed, we already, Wim started with a good overview in the beginning. And then, Ioanna clearly showed how modeling could help in the understanding and in the mitigation part. Combined with other techniques as measuring and data analysis, etc. I will now zoom in a little bit more into other application areas to give you also the full overview. But as a first slide, I want to come back to what we mentioned, what are actually the needs of the utilities. So quantification, understanding, and mitigation is what they want to achieve and are the three actions they want to take. But if we zoom in a little bit more on the quantification needs, quantification really, comes with challenges, and I think it's extremely important for utilities if you want to quantify the emissions and assess your baseline, that this quantification is done sufficiently reliable. For example, it means measuring at the right location to quantify your emissions, for example, because there are so many gradients in reactors, you need to find the good spot depending on your reactor. And then also, if you have a lot of different wastewater treatment plants or very big reactors, it's also very important to have a good return on monitoring investment. You will do measurement campaigns, but is it a good idea to measure for 4 years, for 5 years? How many sensors do you need? So a good return on that is extremely important. And also, all these measurements need a lot of calibration. So you also don't want to burden the staff too much. So there you need to find a good balance. And then understanding, it's Ioanna clearly indicated that how models can help there, but it's important to get value out of the data apart from the quantification, that you really understand why your emissions are being formed, that you also generate generic learnings out of that you can apply in new designs, for example. And then when we come to the mitigation, you want to act as fast as possible. If you have to do trial and error on site, it's very difficult. Also, Ioanna mentioned we will need to do huge investments for implementing these mitigation strategies. You don't want to do this trial and error with those huge investments. So taking into account that is extremely important. And of course, effluent quality and efficiency is important to take into account. So if you look at that, this summarizes a bit the needs for utilities in those three fields. But then on top of that, this is all for existing plants, but also when you are retrofitting a plant or you're building a new plant, you can also prevent N2O emissions or big N2O emissions. So you can also, a clear need for utilities is also take into account the N2O factor in new designs or in planning of new wastewater treatment plants. And there, our models can really help designers and utilities. And I will frame a bit the type of models that we use there and that we developed to help the customers with that. So on one hand, it's indeed the 3D CFD kinetic model, which is indeed based on physics and biochemistry. So it's all integrated into a 3D model, which allows you to really in 3D see the hotspots of those production, like Ioanna mentioned, but also the dissolved oxygen concentrations, ammonia profiles, etc., and gives you a lot of detailed information, which helps a lot also for new designs and retrofits, for example, because you also can change aeration location, mixer location, in and outlets, etc. So that's the one model. And on the other hand, you have the dynamic model, which contains the information from the CFD model. So these hydraulics is taken into account, and that model can give you long-term predictions of N2O and can be used to test mitigation strategies as well. Operational mitigation strategies, changing DO, changing everything you can change in the operational operation of your wastewater treatment plant, and can also be used as digital twins. So a soft sensor for N2O prediction, and on the long term also to do model-based control, for example. So you have seen the needs. How can modeling and the two tools we have there help in all those needs? So in the prevent stage, these models can really help defining an optimal design and defining the optimal operational strategy for this new plant or this retrofit. So before constructing it, already taking into account N2O, minimal N2O by design. And then with the quantification, it gives an idea on the initial emission risks. It can really support your on-site monitoring, defining the right location, and yeah, this gives more additional data of your out of your bioreactor, and refine the quantification because you see the complete picture and not, for example, at one location only. So that's where it can help. And then the understanding, I think that Ioanna made it already very clear. It can really look into 3D and over time into emissions and effluent quality, which gives you a lot of additional insights. And of course, in the mitigation field, you can use the model to really virtually test mitigation strategies without having to test them all in practice. And then it can go to the real-time digital twin. Then last slide that I want to say, it's a little bit about where we are today with the application of those models and where we are going towards. So where we are today, you heard a lot about N2O, but yeah, in general, we use those CFD kinetic models and those dynamic models already for years for the purpose of effluent quality and energy in general. So we already modeled more than 150 plants in 22 countries, and specifically on N2O, more than 30 plants in 7 countries. And we are involved in the 3 stages already in planning, in design, and in operations, and also on a very diverse set of treatment processes. So conventional activated sludge systems, MBRs, MABRs now, granular sludge as well. So that's where we are today, and where are we going? So yeah, you have seen here, it's also clear. It's in combination with monitoring. It's a combination with with measuring, modeling, and mitigation. But we are also working towards a hybrid framework to shorten monitoring campaigns, because seasonal variation is indeed important. But yeah, do you always need 1 year? Or do you need to wait for 1 year to take actions to go to mitigation? So yeah, we're working actually on towards that we can shorten also the measurement campaigns, that you actually can go faster towards mitigation and maximize indeed the investments of your monitoring exercise. And for other processes, we are already running real-time digital twins. And we are also working towards this for our N2O models, that you have the soft sensor for N2O and model-based control. And then I give it back to Wim, who will come with some general conclusions.
Thanks, Peter. Thanks a lot. So yeah, a lot of additional questions are coming in, which is great. So this leaves us some time at the end. After these conclusions, we will have some time for additional Q&A. So also Ioanna is still here, so we can certainly address a couple of more of them. All right. I wanted to add something to Peter's story, but I forgot. I think, let me think. I think, yeah, this is an important one. I just wanted to, what I also wanted to stress is this one. It might seem a little bit weird, enhanced learning through visualization. But what we have seen is that when we work with a lot of plant staff, nitrous oxide, it is not so easy to understand, because we are familiar with linear processes. Nitrification is linear. Ammonia, you add oxygen and it goes to nitrates. It's linear. Nitrous oxide is not linear. It happens at various spots. It goes up and down. It gets consumed, produced. It gets transported. It gets stripped. Now, these visualizations are extremely helpful to really increase the learning curve of plant staff. And yeah, I just wanted to highlight that a little bit. It's beyond mitigation. It's beyond quantification. But it's super important to get people involved. General conclusions. Well, the core needs of practitioners, we feel we need to be focusing on maybe a little bit more as an industry, is return on monitoring investment. It is very important that we do quantification and that we know what the baselines are, and because we know how non-useful the fixed emission factors are. Super important, but we need to ask ourselves the question, okay, how are we going to do this at the global scale for many plants and for the coming decades? So return on monitoring investments is super important. Hopefully, we can also have generic principles and learnings. Yes, it is plant specific, but of course, there are patterns. There are patterns for sure, over aeration, under aeration, carbon limitation or not. And we need to make them visual. Also, N2O work, and we try to convey this a little bit in the webinar, is it should also serve the core focus of a treatment plant, because typically people are very busy. There is a lack of staff. There is even a risk of people leaving, experienced people. So we need to do it smartly. And if it serves the business case, of course, people will be very motivated to continue reducing N2O. The take-homes of Ioanna's story were that there are 2 root causes identified, and you could see in the hotspot analysis that one of those root causes was acting in 2 various spots of the treatment plant. So that was interesting to see. By the way, you will see the recording. It will be shared with you, so you can watch it again. And there is a significant reduction potential expected. Yes, we have used the model to test virtual mitigation strategies, but of course, a reduction of -87% predicted, you can really not neglect. And it was completely in line with on-site experience. That's really important to add. Savings of operational costs are expected as well, and total nitrogen improvements. So as Peter mentioned, we strongly believe in hybrid concepts for the time being. This means you combine data with modeling, and you try to use the best out of both. But we believe this will not only lead to more efficient action in that domain, but also, and that's more important, faster action towards mitigation. Because that's what I mentioned in the beginning of the webinar. There is only one end goal in the end, which is mitigation. And this is really what we should not forget. So the prevention and design, even when there's no plans, no data, is super important. And then we have the quantification, the understanding, and the mitigation. So these were the 4 pillars we tried to highlight. So for the people that need to leave now or want to leave before the Q&A, I would strongly recommend you to watch a couple of our other webinars, because that's where we really go into more detail on certain topics. We even have a playlist on nitrous oxide dedicated, so you can binge watch for hours if you're really a big fan. And also, please do not forget the questionnaire. When you close the window of Zoom, normally there will be a pop-up window with a survey. Please fill that in. If not, please fill in the survey tomorrow when you receive it in your mailbox, okay? So for the people that want to leave or need to leave right now, I really want to thank you a lot for joining. I really hope it was useful for you. And also on behalf of our team and of the people, I also want to thank our guest speaker, Ioanna.